The next video here is on tangent to a curve. No new vocabulary, no new theorems or rules. But we start this way. The moral of the story about the fruit flies in the last video seems to be that we should define the rate at which the value of the function y equals f of x is changing with respect to x at any particular value x equals a to be the slope of the tangent to the curve y equals f of x. And that's what we saw. We saw the curve, we saw secants to the curve, and we saw that if we wanted to know exactly what the rate of change was at a particular point, in this case we call it a, we really needed to be focused on the tangent line. But the question becomes then, how are we supposed to define the tangent line and find its slope when we only know one point? Especially when our whole idea of slope is based on having 2 points by which to calculate it. We're very used to the y2 minus y1 over x2 minus x1 formula for slope, but we want the slope at just 1 point. Well, the solution to that question was found by Pierre de Fermat in 1629, and that solution to be proved to be one of this century's major contributions to calculus. His method went like this. First, start with something you can do, with something you can calculate, namely the slope of a secant. You can calculate a slope of a secant through a point P and then some point Q that's nearby P on the curve. And then we find the limiting value of the secant slope, if it exists, as Q approaches P. So if we take Q and take it towards P using some limiting function, then we are approaching what the slope of the tangent would be. And we're going to define the slope of the curve at P to be that number, whatever the value of this limit is. And then we're going to define the tangent to the curve at P to be the line through P with that slope that we found here. So I put a white space in here so I could kind of graphically explain what was going on. So this will be our grid. And let's say we have, that wasn't very good. Let's say we have some kind of function here, and we're very, very interested in the slope of the tangent line here at P. So I'm going to draw the tangent line here in red. And that was a little too close for comfort. How about this? Nice. So there's my tangent line. I want to know what the slope of that is. Can't find a slope if I only have 1 point. So here was what Fermat said to do. Pick another point on the curve somewhere nearby P, but a little ways away, and call it Q, and calculate the slope of the secant line, the one that goes through point P and Q, and find that slope. And then use limits to send Q toward P, so that maybe next Q would be here, and now you've got a different secant line, and that slope would be a little less steep. And then maybe move Q here, and then that slope would be a little less as well. And you move Q towards P in such a way that eventually Q might as well be on top of P, and your slope of the secant approaches the slope of the tangent. So that's the idea. Here's an example where we can show that in action. We want to find the slope of the parabola y equals x squared at the point 2, 4, and write an equation for that tangent line to the parabola at this point. So what does this mean? Let's make a little graph here of y equals f of x. And it's going to be something like this, right? And we want to know the slope of the parabola at 2, 4. So here's 1, 2. Actually, that's not going to be about right. Let's see. 1, 2. There we go. And then 2, 4 would be right up in here. So the slope there would be the slope of the tangent, and that's point P. So what we can do then is bring this parabola out a little bit further and find another point on that parabola Q, and we want to take Q toward P with limits. Okay, so how are we going to do that? Well, Q doesn't necessarily have to be a specific static point. It can just be a little bit of a space away from P. Let's take a look at the Desmos graph of this situation before we go any further. So here's the graph in Desmos. The blue function is y equals f of x. Here's our point P at 2, 4. And here's a point Q, a little bit of a space away from P. And we're going to watch what happens as Q approaches P. The secant line is going to approach the tangent line, and we can see the space between them getting smaller and smaller and smaller until we're at 0.01 away. And then this basically looks like a tangent graph. If there's no space between them, the line goes away. But here's what it is. There in purple, that's the tangent line. And then let's move Q out a little bit. We can watch the red secant line approach the purple tangent line. So that's what we're going to try to do here in this example 3. So let's start like this. Let's say we know point P is 2, 4. Let's define Q to be just some amount of space away. So that would be what? 2 plus some imaginary or some number. Let's call that number h. That seems to be pretty traditional. And then the y value there would be 2 plus h into the function. So that's going to be, in this case, 2 plus h squared. Okay, so the slope of the secant then, I'm going to call it, let's actually call it, how about m, actually the squared went away. Let's call it m sec. And that secant is going to be the change in y value over the change in x value. So the change in y value, well, first we have the 2 plus h quantity squared. That's the second y, and then minus the first y is 4. And then the denominator, we have the change in x. So it's going to be a 2 plus h minus, and then the other x value would be 2. So what does this work out to be? Well, 2 plus h quantity squared is h squared plus 4h plus 4, and then we have our minus 4 there. In the denominator, 2 plus h minus 2 becomes h, and we can continue to simplify. 4 minus 4 makes 0, so we have h squared plus 4h all over h. And then in the numerator, it looks like both terms have a common h, so we can factor out that h and have left over h plus 4 over an h, and then that h is going to cancel, isn't it? Leaving us with h plus 4. So the slope of the secant line, here drawn in green, is h plus 4, or 4 plus h, depending on the order in which you did your work here. So what we want to do then is figure out what happens as the point Q approaches the point P of the secant slope. So as Q approaches P, the space between those 2 points is actually approaching 0, right? Because we want to bring Q toward P. So this limit is equal to the limit as h approaches 0, and we calculated the secant slope here on the left as h plus 4. So if h is going to 0, then h plus 4 is going to 0 plus 4, which is 4. And so we would argue then that the slope of the parabola at y equals x squared and the point 2, 4 is 4. And we'll find out a little bit more about this process in the next video, slope of a curve.